Hello students, welcome to lecture 4 of rotational dynamics. The topic that we are going to see today is minimum safest speed to move in well of death. For your reference, I have attached a picture of well of death on the right hand side of the screen where you can see a motorcycle undergoing a circular motion in well of death. Now, to undergo a proper circular motion in this well of death, the vehicle must maintain a certain minimum speed, because if the speed of the vehicle falls below this minimum safe speed, then the vehicle slips down and it falls. So to continue the circular motion, the vehicle must have a certain minimum speed, and today we are going to derive the formula for that. To do that, we first have a look at the free body diagram of the vehicle, where we can see that the forces acting onto the vehicle are normal reaction towards the center. This normal reaction is exerted by the well on the vehicle. And then we have the static friction, which acts upwards, and there is a weight which is acting downwards. So we can see that this static friction is basically balancing the weight and preventing the downward slipping of the vehicle. It is preventing the downward slipping of the vehicle. So from this fact, we get our first equation, which is nothing but Fs is equal to mg. Fs is equal to mg. Then, as we can see that the normal reaction is acting towards the center, therefore it must be providing the necessary centripetal force that is required to undergo circular motion. So we can write down N is equal to mv square by r, where v is nothing but the velocity with which the vehicle is undergoing the circular motion, and r is the radius of the circular path. To move further in the derivation, we use the fact that the static friction has a maximum value, and we call it limiting value of the friction. So whatever static force is acting between the well and the vehicle, it must be less than or equal to limiting friction. And we know that the limiting friction has a formula μs into n. Therefore, whatever friction force is acting between the vehicle and the well, it must be less than or equal to μs into n. Now we just saw that Fs is equal to mg and n is equal to mv square by r. We substitute these two values in the equation on the left hand side, and we get mg less than or equal to μs into mv square by r. We cancel out m and we get rg upon μs is less than or equal to v square, or v square is greater than or equal to rg upon μs. So from this we get v must be greater than or equal to under root rg upon μs. So finally we get the value of minimum speed as v minimum is equal to under root rg by μs. So if the vehicle has to safely undergo circular motion in the well of death, then it must maintain a minimum speed, which is calculated by the formula under root rg upon μs, where r is nothing but the radius of the well, g is nothing but the gravitational acceleration, and μs is nothing but coefficient of static friction. Thank you. Okay students, let's move on to the next topic, and that is nothing but banking of roads. In lecture number 3, we discussed the maximum speed with which the vehicle can take a circular turn on horizontal rough road. And in that video, we saw that the maximum speed on horizontal rough road while taking a circular turn is under root μs rg. And in that derivation, we used a fact that to take circular turn, the friction between the tires and the road was providing necessary centripetal force. But the tire is not evenly rough. Also, the road is not evenly rough. As we move ahead, as the speed changes, the friction might be affected, and therefore friction is not reliable. It also has an upper limit. Therefore, we cannot depend on friction while taking turns. So to avoid this dependence on friction, what we do is we tilt the roads. Now what happens when the roads are tilted? What happens when the roads are tilted? The answer to this question you can see in the diagram on the left hand side. So when the road is tilted, you can clearly see that the normal reaction perpendicular to the road can now be divided into two components, that is n cos theta and n sin theta, when the road is tilted by an angle theta. Now, don't concentrate on n cos theta, but if you look at n sin theta, you can clearly see that it is acting towards the center of the road and therefore helps us to provide the necessary centripetal force that is required to take a circular turn. So, by using this concept, that is tilting of roads, we can remove the dependence on the friction, and even without friction, we can use a component of normal reaction for our help while taking circular turns. This concept of tilting the roads to ease the turning of the vehicle is called as banking of roads. So the derivation that we are going to do over here is the derivation of expression of angle of banking, but this angle of banking is for frictionless roads, which means there is no friction. Now, we have the same diagram that we saw earlier on the left hand side, and we can see that the vertical n cos theta force is balancing the weight, and therefore we can write down n cos theta is equal to mg. Now, as we discussed earlier, we do not require friction to provide the centripetal force. Rather, a component of normal reaction helps us and provides us with the required necessary centripetal force. And in this case, from the diagram, we can see that the sine theta component provides us the centripetal force. Therefore, n sine theta is equal to mv square by r. So v is nothing but the velocity of the vehicle with which the vehicle is turning on the circular road, and r is nothing but the radius of the road on which the circular turn is being taken. So we have two equations. N sine theta is equal to mv square by r and n cos theta is equal to mg. If we divide, then n sine theta upon n cos theta, we get it equal to mv square by r upon mg. N and n cancel on the left hand side, m and m cancel on the right hand side. Sine over cos is tan, and we get tan is equal to v square by rg. So from this, if we take tan onto the other side, we have theta is equal to tan inverse of v square by rg. So this is the formula for the angle of banking theta. Angle of banking theta. So you can remember any of the formula. Either you can remember tan theta is equal to v square by rg, or you can remember theta is equal to tan inverse of v square by rg.